Okay, so I want to talk a little bit more about simple harmonic motion, and again assuming a certain knowledge of trigonometric functions here and trigonometric graphs in this lesson. So quick reminder of simple harmonic motion. An object is moving with simple harmonic motion if its acceleration is proportional to its position but has the opposite sign. So if its acceleration is proportional to its position but has the opposite sign. So when the position is positive, the acceleration will be negative. When the position is negative, the acceleration will be positive, etc. They're proportional. That means as one grows, so too does the other. Okay. So that's what we mean by proportional and in the opposite sign. So again, if I just take a quick graph here, I have a picture of an object here moving with simple harmonic motion. This little object here, E, moving up and down. You can see it's just moving around up and down between 2 points. And if I take, this is its starting point when it's at 0. We'll take its starting point at 0 and on the way up. So if I take its starting point here at 0, it goes up to 1, it goes down to -1, and then it returns to position 0. And then it just repeats that over and over again. That's what we call one complete period. From 0 to 1 to -1 back to 0. That's one complete period. That is the thing, it just keeps repeating. And what's it doing? Well, as it's moving passes 0, it starts kind of slowing down until it stops at 1, and then it speeds up, and it starts slowing down again until it stops at -1. It speeds up till it gets to 0, slows down till it gets to 1 and it stops, speeds up till it gets to 0, slows down till it gets to -1 where it stops, speeds up till it gets to 0. So one thing to note is acceleration is always in the direction of the center. It's always in the direction of the center. Okay, sometimes that acceleration is positive, sometimes it's negative. Okay? When its position is positive, its acceleration up here, its acceleration aimed towards the center will be negative. And when position is negative, its acceleration aimed towards the center will be positive. As it gets further away from 0, the acceleration increases. As it gets closer to 0, the acceleration decreases. When it gets to 0, the acceleration is actually 0. And it's at that point where its velocity will be greatest. It speeds up till it reaches its maximum speed at 0, and then it slows down as it moves out towards the extremes. So it speeds up, maximum speed at 0, slows down till it gets to the extreme points here. And if I kind of start thinking about getting some kind of graph of this, graphing its position against time, so where time is on the horizontal axis, position on the vertical axis, there's a point there. That point is copying the behavior of the other point. It's telling me where it is at some particular time. And if I just put a little trace on that point, you will see that point is moving in a sinusoidal fashion. We have essentially got a sine wave, which can be kind of drawn. We can draw a sine function here. There it is. It would continue along that. Okay, I've just taken one period of it here along here from 0 to 2 pi seconds. So this is simple harmonic motion. It can be described using a sine or a cosine curve, depending on, how we want to think about it. Again, looking at this before, we have ways of figuring out the amplitude of this curve. We said before the amplitude, remember the things that are variable here. S is a variable, t is a variable, everything else really is a constant in this. T is the time that's passing, displacement is changing from a fixed point. Okay, that position of equilibrium, that's the fixed point. So displacement here is a sine omega t plus alpha. Its amplitude we said before, will be the absolute value of whatever that a is, that coefficient in there. The period here, and period we're going to use for simple harmonic motion, we're going to use the capital T, the letter capital T for period. And we said in our previous lesson that the period always is 2 pi divided by the absolute value of the coefficient within the argument here. So the coefficient within the argument is omega. Okay, so that's the period and amplitude. So you have to be able to look at questions where they describe the displacement of an object from its position of equilibrium after some time, and you should be able to identify what the amplitude and the period are if they give you the trigonometric function. Now, my formulas for simple harmonic motion can be found in your formula and tables booklet on page 54. Okay, and a simple harmonic motion, this is given here. Simple harmonic motion, objects moving with simple harmonic motion can be described with a sine function, but you got to remember that could also be a cosine function. They've just put the sine function in there. Also, it gives me this formula for finding the period of the function. T is equal to 2 pi over omega. Okay, remember T means the period, how often it takes to repeat itself. Things moving with simple harmonic motion go back and forward or up and down forever and ever. Okay, and that's the idea. The acceleration is always proportional to its position, but has the opposite sign to its position. So if position is positive, acceleration is negative. If position is negative, acceleration will be positive. The acceleration is always directed towards that center of the oscillation. It's always directed towards in here. Okay? Maximum velocity right in here in the center. Velocity of 0 out here at the extreme points. Maximum acceleration out at the extreme points. Acceleration of 0 at the center. Okay? So get used to that. Make sure you can find the amplitude and the period from an object moving with simple harmonic motion.